Hi, in this video I'll solve this question of finding the inverse Laplace transform of this function right here. Capital F of s is equal to ln of 1 plus 16 over s squared. So for these problems, especially whenever I see an ln, I always want to do the algebra to sort of expand or simplify the ln so that the inside of it is as simple as possible. So right here, I can do the common denominator of the inside. I get s squared plus 16 in the numerator, s squared in the denominator. And now since it's the logarithm of a division, I can break it into a subtraction of logarithms. And then another property of logarithm allows me to bring the exponent 2 right here to the front of the ln. All right, so I've simplified the logarithm as much as I can. And now I'm going to do inverse Laplace by looking up the table and, oh shoot, that didn't work. Here's a typical short Laplace transform table that most people use, and there's no ln in it. Okay, let's go look at a longer table. Here's a longer table, and no ln either. Well, now what? For inverse Laplace problems, if the function itself is not really on the table, you should always look at, let's say, is it a product of two things so that we can use a convolution theorem, or is it the derivative of something or integral of something, or vice versa, what is the derivative of it and what's the integral of it? And then it's one of those three things, then we can use the appropriate formula. Well, in this case, it doesn't look like we can use a convolution theorem. So let's see if we can use either the integral or derivative. So in other words, the flip side of it is look at the integral of this and look at the derivative of this. Well, I tried looking at the integral of it, and I know, yeah, integral of ln is probably like the hardest integral ever. So I guess I'm not going to look at the integral of it. I'm going to look at the derivative of it. Derivative of ln of s is 1 over s. Derivative of ln of s squared plus 16 is 1 over s squared plus 16. And then by the chain rule times the derivative of it, which is 2s. And look, both of these are on the table. The first inverse Laplace is a cosine. And the second inverse Laplace is a constant, is 1. So both derivatives are doable. Then I look at the formula for inverse Laplace of derivatives, because one exists, and it's this one. The formula says that if the inverse Laplace transforms exist at all, then they satisfy this relationship. Well, that means that if we can do the inverse Laplace of the derivative, then we plug it into this formula, we will then get the inverse Laplace of the function f itself. Okay, so at this time, I'm going to prove this theorem. I'm going to prove this formula. But if you're not interested in the proof, go ahead and scroll forward and move past this part. Use the chapter markers on the YouTube scroll bar. I'm going to prove this by using the definition of Laplace transform itself. Since we assume that the inverse Laplace of capital F exists, I'm going to write it as little f. And I'm going to remind you that the little f function is in the t domain, while the capital F function is in the s domain. So let little f of t be such that the Laplace transform of it, first of all, exists. And as just a reminder, I'm going to write down the conditions for the Laplace transform of f to exist, and that is that f of t is piecewise continuous And f is of exponential order, meaning it doesn't grow faster than every exponential function. It will have to be bound by some exponential function. It's less than or equal to some exponential function, and the general form of exponential function is e to the ct times some constant. Right, the Laplace transform of little f is capital F. What does it mean for the Laplace transform of little f to be equal to f of s? By definition of Laplace transform, that means capital F is the integral, and this is the definition. And by the way, the reason why the whole integral here is a function of s and not of t or of both s and t is because it's a definite integral. So after you integrate with respect to t and you plug in the limits, the t's are gone. There's no more t in the expression. The only thing that would be left is s. So that's why it's a function of s. Right, now, what is the derivative of f? The derivative of f is f prime of s is equal to derivative dds of this integral. How do we differentiate an integral? Well, in this case, since the inside of the integral is e to negative st times f of t only, the function e to negative st is continuous and its derivative with respect to s is continuous. So we're allowed to switch the order. We're allowed to switch the order between the integral and the derivative. We're allowed to flip it around like this. Now, how do we differentiate this? This function f of t, even though it is a function, but it's a function of t, not of s. As far as s is concerned, it's like a constant. It's an expression written with a bunch of t's, so when s changes, that expression doesn't change. So in the s world, f of t is a constant. That means we can factor it out. We can factor it outside of the derivative. And we end up with this. Now we differentiate. This derivative, again, think of t as a constant. So the derivative of e to negative st is e to negative st times, and now the chain rule says we need to multiply by the derivative of the inside here and the derivative of negative st with respect to s is negative t. So the whole thing becomes this. And then I can rewrite this as, yeah, this looks familiar. This is a definition of a Laplace transform, right? Integral from 0 to infinity of e to the negative st times something is the Laplace transform of that thing. So this whole thing is the Laplace transform of negative t ft. And we started with f prime of s like this. So capital F prime is equal to the Laplace transform of negative t ft. Now I'm going to take inverse Laplace both sides. Then the inverse Laplace of the left-hand side is going to be equal to the inverse Laplace of the right-hand side, which just cancels out the Laplace, negative t f of t. And what is little f of t again? Little f of t is the inverse Laplace of capital F. And now I divide both sides by negative t, and actually going to write this over here. And there we go. I have a formula that relates the inverse of a derivative, the inverse Laplace of a derivative, with the inverse Laplace of the function itself. So whenever I have the inverse Laplace of derivative, I can use this formula to compute the inverse Laplace of the function. So here we are. We arrive here. We have a formula for computing the inverse Laplace of function given the inverse Laplace of the derivative. And our capital F is this ln, which we've already done the algebra to simplify to this. Let's now compute the derivative of capital F. Derivative of ln is 1 over. And by the chain rule, I have to multiply by the derivative of the inside, which is 2s. Like this. What's the inverse Laplace of this? Let's bring out the table. This first term, I can see it matches the formula for cosine. So the inverse Laplace of the first term is 2 times cosine of 4t, where k squared is equal to 16, so k is equal to 4, minus 2 times. The inverse Laplace of 1 over s is just 1. And now plug in this formula. Negative 1 over t times all of this. And I'm done. If you want to be nice, some people don't like having a negative in front if they don't have to. And there's a common factor of 2 inside the brackets. So if you want to be nice, you can factor out the 2 and multiply the negative on the inside to arrive at 1 minus cosine 4t. Box it up. Hope that helps. If you have any questions or comments, put it in the comments below. Like, share, and subscribe for more contents. And thanks for watching. Bye.